Manage the rate of sugar. This is like
Okay, class, I'm glad to see you to for the first lesson in that important unit. I have to tell you this is the most important unit of the whole year. It is so important. We will dwell in it for 6 weeks, for the next 6 weeks. That unit will include chapter 15, chapter 17, and chapter 16 in that order. We will cover 15, 17, 16. So I'm going to ask you to pay very, very close attention from the beginning. I will say a lot of things in that first lesson that you already know. Please be patient with me because we have done some equilibrium on the first year. So listen carefully. They are all background we need for the whole unit. Okay, like I said, this is chapter 15, chemical equilibrium. The objectives. We will be able to write the equilibrium expression for a balanced chemical equation, whether heterogeneous or homogeneous. Numerically evaluate Kc or Kp from a knowledge of the equilibrium concentrations or pressures of reactants or products, or from the initial concentrations of the equilibrium concentrations of at least one substance. Your homework is the first quest is general and gas phase equilibrium 01. So we will have 2 quests for chapter 15, and we will also have a lab for chapter 15. Okay, chemical equilibrium. When you say the word equilibrium, what really comes to your mind is equal, it is balance. But I have to tell you from the beginning, equal does not mean that the amount of reactants equal the amounts of products. It is just a balance. What it means is when the rate of the forward reaction is equal to the rate of the reverse reaction. The forward reaction when you go from left to right, the reverse reaction is you go from right to left, because most reactions do not go to completion. They are reversible reaction. They can go from reactant to product, and the products can go back and produce reactants. There is no net change in the concentration of reactants and products with time. It means the amounts are not equal, but the amounts are constant. And if I to just imagine you have an island, okay, and then you have the mainland. You have a bridge connecting the island to the mainland, and you have a bus taking people from the mainland to the island and back and forth. Even though you don't have the exact same people in both places, the island and the mainland, but it gets to a point where the amount of people in each place is constant. They are not the same people, they are not equal, but the amount in both places is constant. Because the bus is dropping 20 people at the island, the bus is taking 20 people back to the mainland, it is constant. But it's not, they are not the same reactant, the same products, and we don't have the same amount of people on the island and in the mainland. The system is said to be in dynamic equilibrium. Dynamic means movement. You may look at it and see nothing is happening, but there are things going on. Just imagine you have a beaker closed with boiling water, you have some water vaporizing, at the same time you have some condensing. Okay, when the rate of condensation equal the rate of vaporization, that's what we have, a dynamic equilibrium. All right, let's move on. Equilibrium constant. Okay, equilibrium constant. Let's see how do we derive it. Let's say we have the equation dinitrogen tetroxide reacting to produce nitrogen dioxide. This is the forward reaction. Forward reaction. And if we have to write a rate for the forward reaction, we write rate equal the rate constant lowercase k time the concentration of the reactant. This is the rate constant. How about if we have the reverse reaction? We have 2NO2 going back to produce N2O4. If they ask you to write the rate for this equation, it is rate equal the rate constant lowercase k reverse time the concentration of the reactant raised to this is the order. This is an elementary step. So this is the rate for each one of them. But at equilibrium, we said rate of the forward reaction equal rate of the reverse reaction. Therefore, we can write that rate constant time that reactant equal the rate reverse time the other reaction. So if we, okay, let's go back here. If we put our rate constant on one side of the equation, we can write rate forward over rate reverse equal NO2 squared over N2O4. If you crisscross right here, you will see it is the same thing here. Alright? And because this is a constant over a constant, we can write, let me see right here, we can replace those constants by KEQ equal this product. So those are two constants. We replace it by a capital K. Okay, rate constant is a lowercase k, equilibrium constant is a capital K. So you have to be careful when you write your K's. Lowercase k, rate constant, and equilibrium constant, a capital K. When we put KEQ, equilibrium constant, it is more generic. By the end of the unit, you will know more or less 9 Ks. Alright, so this is a generic way for all of them. Okay, equilibrium constant. So as you can see, it is the product of the products raised to their coefficient over the product of the reactants raised to their coefficients. This is the formula for equilibrium constant, as you can see right here. If we have a generic equation, lowercase a is the coefficient time capital A, the reactant, plus another reactant and its coefficient, yield, and a capital C and its coefficient plus capital D and its coefficient. To write the equilibrium constant, you take the product raised to their coefficient over the reactant raised to their coefficients. Now, as you can see, this is another version. The way you write the K subscript C is not, it just means concentration. You are using concentration. You can also use pressure. You can call it KP. So we already learned 3 different Ks. Okay, you can write KEQ general, K subscript C for concentration, and K subscript P when you are using pressure in that formula. As you can see, you have to be very careful when you write. When you have a square bracket, you know you are dealing with concentration. So you cannot use square bracket when you are using pressure. You will have to use a capital P. So do not use square bracket if you are using pressure. The square bracket is just for concentration. It is for molarity. Now, what are the equilibrium expression for this equilibria? So let's start practicing right now. If they ask me to write the equilibrium expression, I'm going to write K. If I am using concentration, I can put Kc. If I am using pressure, I will put Kp equal. I write down, why don't I put my fraction bar? I know I have only one product. I will put my square bracket for concentration. I know I have to use the coefficient as exponent. I will put the 2 here, and I put my substance right here. Okay, over bracket. I have 2 of them. I can even, just to make sure I include everything, I would put the square bracket for each one of them. Just to make sure I don't forget the exponents, I would just include them right now. This is a 3. And then I write down my substances here, which is H. This is the expression. I can do the exact same thing with pressure. With pressure, like I said, I can, why don't I do it with pressure? I can write down Kp equal, now I'm not going to use bracket. I'm going to use capital P for pressure. I will put the substance as a subscript here, NH3, and I'm going to use still the exponent for the P over, I use capital P, this is my N2 as a subscript, and I put, when it's 1, I don't have to put a 1, and then times, I have another pressure subscript H2 raised to its coefficient. It depends what I have, if I have pressure or concentration. So I do the exact same thing with the second one. So I write down K, let me do it only with concentration, since you already see how to do it for pressure. Kc equal, and I see I have only one product. I will put SO3 raised to its coefficient over, this is SO2 raised to its coefficient times O2 raised to its coefficient, which is 1. I don't have to write. Okay, we set. Next. Now, write the equilibrium expression for the following. I don't think I really need to do that. We just did the exact same thing. Okay, so make sure you use every single the products, you multiply them, you raise them to their coefficients. So you practice this on your own. Okay, now one thing I need to say, all right, listen carefully. In the equilibrium constant expression, you do not include pure solids or pure liquids. If you say S for solid, it's a L for liquid. You do not include those. You only include if you say aqueous or if you say gas. Okay, for gas you can use concentration or you can use pressure. For aqueous you will only use concentration. Now it says here, write the expressions for K and Kp for the following process. Sometimes they give you a word equation. You need to know how to write a balance equation for that word equation. It said the decomposition of solid phosphorus pentachloride. What don't 2 liquids? What don't I start writing? It says solid. It's a phosphorus. It's a pentachloride. So I will write PCl5, and it is important that I put that solid. 2 is a decomposition. That's when I have only one reactant. 2 liquid phosphorus trichloride. It is P, it is Cl3, in parentheses it says liquid, lowercase l, and put plus, it's a chlorine gas. I need to know it is a diatomic molecule, and I put gas. And I have to make sure I have a balanced equation. So I will have 1 phosphorus and I have 5 chlorine. It is balanced. And they asked me to write the expression. So why don't I come here and let me just move it right here. I write down the expression. It is, they asked me for Kc. I write down Kc equal, I put my fraction bar, I put bracket, there are 2 products, Now, you have to be extremely careful. Am I going to include PCl3 in that expression? No. No. So this is just Cl2 to the first power over. Wow, look at this. This is a solid. I do not include it. So my expression, it is bracket Cl2. It is the concentration of Cl2 and I'm done. Alright? So what do I do for the Kp? I do the exact same thing. It is K subscript P equal, I do not use square bracket, I just put PCl2 to the first power, which I don't have to write. Okay, we are done with this. There is another example here. It says deep blue solid copper sulfate pentahydrate. Solid, it is copper 2 sulfate. So I need to know how to write my formulas. It is copper 2 sulfate is SO4. SO4 is 2 minus. Copper is 2 plus. 1-to-1 ratio. It's a pentahydrate. When I'm writing a hydrate, I put a dot for the water, and then penta give me 5 hydrate. This is my water. Okay, deep blue solid, very important. Tell me it is a solid. Is heated to drive off water vapor. Water vapor. So I write down my water, and I already see it is 5 water. But it's a vapor. It is a gas. The difference between a gas and a vapor, a gas is a gas at room temperature, and a vapor is a solid or a liquid that had been changed into a gas. But I still write this is a gas, and to form the white solid copper 2 sulfate, this is my CuSO4, and it is solid. Very important. So my Kc equal, this is a solid. Okay, I'm not including it in my expression, and then this is my bracket. This is water gas to the 5th power over. This is a solid, I don't include it, and I'm done with Kc. And you do the same thing with Kp equal pressure. You have your water, pressure of the water to the 5th, and I'm done. Okay, let's move on. Relationship between Kc and Kp, they are not the same. No, they are not the same. You cannot interchange Kc for Kp, so listen carefully. Okay, if you remember your ideal gas law, PV equal nRT. Therefore, I can write P equal N over V over time RT. Number of moles time volume give me molarity. Molarity is concentration. It is bracket. It is concentration. So I can write, if I put a K, I can write Kp equal Kc for the concentration. RT, listen carefully, delta N is the change in the number of moles of gases in that balance equation. It is number of moles of gases from the product minus the number of moles of gases in the reactant. It can be negative. It can be negative. Delta N equal number of moles of gases from the product side minus the number of moles of gases from the reactant. And remember I said gases. Now, let me tell you that is very common. Very, very common. Students forget, always forget. What comes here, is that the C or is that the P? Students interchange them. They said, I cannot remember if it's Kc equal Kp time RT delta N, or is it Kp time Kc equal Kc time RT delta N. I will remind you, you have to always be politically correct. Make sure you are politically correct when you write that formula. Okay? And then pressure is usually in atmosphere. That means your R in that formula will be 0.0821, not the 8.314. The energy R. In this formula, you are using 0.0821 because unless you have your pressure in kilopascal. Okay? But usually we are talking about ATM here, so it is 0.0821. Alright, let me see. Now, why don't we pull out your calculator, please? Help me. I need to get to a good final point. Relationship between Kc and Kp. The reaction for the formation of nitrosyl chloride, and they give you the balance equation here. They were nice to give it to you. Was studied at 25 degrees Celsius. The pressures at equilibrium were found to be, and they give you the pressure for each one of them. Pull out your calculator, please. You have the pressure for each one of them. Calculate the value of Kp for this reaction at 25 degrees Celsius. So I write down my Kp equal. Guess what? You get a whole point for writing the expression before you plug any numbers. I know you like to go fast. I know you like to go straight to the answer. You will lose 1 point in the AP exam if you don't write the expression. So don't put number yet. Write the expression. So I write down Kp equal. I look at my balance equation. Talking about P. I will put the pressure of NOCl raised to the second power. That's the only product I have. Over, and they are gases. I have to be careful with the state. Pressure of NO to the first power time pressure of Cl2 to the first power. Therefore, right? To the second, thank you. NO to the second power, thank you. Therefore, Kp equal, now I plug numbers. Remember to write the expression first. So the pressure for NOCl is 1.2. And then it says to the second power, it is squared over the pressure of NO, which is parenthesis 5.0 times 10 to the negative 2 to the second power times the pressure of Cl2, which is 3.0 times 10 to the negative 1. Remember, sig fig count. And this is to the first power. Therefore, you do all of this on your test. Write the expression, plug the numbers, and then write your final answer. Kp equal, say that again, 1920. The good news for you, I hear some people say it's not right. The good news is no unit for K. Okay, no unit for capital K. The unit is extremely important for the rate constant. Very important for rate constant, but no unit for capital K. Alright, let's see if we can do one more page. Check the answer. Okay, I heard it's not the right answer. Okay, the answer is yes, it is right. 1900 something. Okay. Alright, let's go next to see if I can stop at a good point here. Using the value of Kp obtained in the previous exercise, calculate the value for Kc. When they don't tell you anything for the K, it is Kc. Okay, Kc at 25 degrees Celsius for the reaction. I will stop after this problem, so help me finish this one. All I have to do is get my answer. Let me write the formula first. I write down Kp equal, this is Kc time RT delta N, lowercase n. Therefore, Kp from now, the other problem is what? 1900 what? 20 equal Kc that I'm looking for time my R is 0.0821 times my temperature in Kelvin. Temperature in Kelvin is 298 Now I look at my balance equation. It is 2 moles of gases. O minus 3 moles of gases give me -1. -1. Therefore, Kc equal 1920 over 0.0821 times 298 close parenthesis to the -1. Therefore, do the same thing on your test. Do the same thing. Kc equal what? 46,000 46,990. Okay, you can celebrate. No unit. That's what you put in a square and for your final answer. Okay, so this is not a good point, but you gave me the signal that my time is up. So I would advise you to really to have a good start for that unit, because your quarter grade will really be determined mainly by this unit, because it's 6 weeks out of the quarter. So I hope you enjoy your day, and then let's have fun with equilibrium. Okay, take care. Bye.